I'm going to show some results from UCoMP wave observations to get the global coronal magnetic field maps, perhaps the routine measurements of global coronal magnetic fields. We know that the coronal magnetic field is very important because it's related to thermal eruptions and coronal heating. And the magnetic field of the sun are connected in each atmospheric layers. So we need to, if we want to understand the different physical processes happening in the solar atmosphere, that requires the entire information of the whole atmosphere magnetic field. But up to now, we can only do routine measurement on the photospheric level. There are several different attempts to measure the coronal magnetic field, but they are still very difficult. For example, we can use spectral polarimetry calculations to retrieve the non-offset component, or we can use radio observations to get the strong magnetic field in very low corona. And of course, there is also the method called coronal seismology, which is a combination of MHD wave theory and actual wave observations in the corona. I would like to separate coronal seismology into two different types. The first one, we can call it 1D coronal seismology, which is, for example, here on the left, during flare, we can see the flare triggers the oscillation of the local oscillation of the coronal loops. And by analyzing these oscillation patterns, we can get the we can relate to the wave parameters with the coronal parameters, physical parameters such as magnetic field. So in this case, we can get the magnetic field in that oscillating coronal loops, but this is usually just a single value for that coronal loop. And this kind of oscillation, because they are triggered by flares or other eruptions, so they are not always, they cannot always be observed. And so if we want to use coronal seismology to measure the global magnetic field in the corona, we need some more ubiquitous waves. So luckily from COMP or UCoMP, we can see this kind of propagating waves, and they are almost everywhere in the open corona. And if we apply the coronal seismology method to this kind of waves, we should be able to retrieve the 2D distribution of the coronal magnetic field. So this method is called 2D coronal seismology. And so here on the right, this movie shows the Doppler velocity time series observed by COMP. So you can see this black and white, they are the blue and the white shift. And they are propagating outward, and they are almost everywhere in the field of view. And now we know that this kind of velocity fluctuations, they are pink or alternate waves. And we know for pink waves, their phase speed is expressed as the left equation. But on the corona condition, if we assume that it's no plasma beta in corona, then the BI and BO, which refers to the magnetic field inside and outside of the flux tube, they are almost the same. And because of the spatial resolution of the instrument, both for COMP and UCoMP, it is not likely that we can resolve a single flux tube. So actually, under this kind of condition, the density we derive from COMP or UCoMP observation can be regarded as an average value inside and outside of flux tube. So in this case, we can simplify the original phase speed of pink waves to the right one. This is very similar to the orange wave equation. So from this equation, we see that if we have the phase speed of these waves in the corona, and we can also measure the density in the corona, then we will immediately obtain the magnetic field strength. So that's the basic idea of the 2D coronal seismology using COMP and UCoMP. And so we use the wave tracking technique introduced by Richard this morning. we can obtain the wave propagation direction, which also refers to the magnetic field direction onto the plane of sky. And we can also calculate the phase phase. And because COMP and UCoMP can observe using these two ion 13 density-sensitive non-ratio. So we can use this non-ratio to diagnose the electron density in the global orbiting corona. And combining these two, we can get the magnetic field strength in the corona. And because we have mentioned the wave propagation angle, because these waves, they are transverse waves, so they are propagation along the field line. So the wave propagation direction also indicates the plane of sky direction of the magnetic field. So using this 2D corona seismology, we can get both the magnetic field strength and the direction. We think it's plane of sky component in this work, but we will see that it's not actually on the exact plane of sky. And so this is what we did using COMP observations. And what about UCoMP? For UCoMP, because it has a larger field view and a better spatial resolution, and more importantly, it has a much improved Doppler velocity data. So we can obtain. So we have already obtained like 64 corona magnetic field maps within 6 months, from February to August 2022. And this this implies that UCoMP already has the capability to do this kind of routine measurement for corona magnetic field using wave observations and applying the 2D corona seismology. And we can also get some current magnetic field maps similar to what we did for photospheric magnetogram. So we chose the east and the west hemisphere of each corona magnetic field map, and we stack. We get one strip of these. It's the latitudinal distribution of the magnetic field, and we stack all of these strips of the magnetic field together, and we can get a corona magnetic field current map, like the one in the lower right corner. And this is the corona current B map average between 1.1 to 1.15 solar radii. And one important thing about this method is we can the magnetic field measured in polar regions are as accurate as the rest of the corona. So we do not have the problem of extrapolations like what people did from photospheric magnetic field. Also, we can do a comparison between the global corona magnetic field with the photospheric magnetic field derived from STSW, and we can see that in most regions, the strong patches with strong magnetic field strengths have a very similar distribution, and this is just the result for one solar rotation. And because we have a half year's observation, we can almost have a routine measurement for several different solar rotations to get different movies like this. So we have already demonstrated what we can do with the UCoMP wave observations and the 2D corona seismology, but what exactly is the measured magnetic field? And because we know for all optically thin observations, they will all be impacted by the non-exact integration effect for UCoMP, COMP, but also for imaging observations such as from AIA and those spectral observations from the ice. So if we simply assume that the magnetic field map we derived from UCoMP is the exact plane of sky component, we can do a comparison between the observation and model. So here on the left, this is the observed magnetic field strength, and on the right, it is we choose an exact slice of plane of sky from the PFS model, and we can see in many regions here a very large difference, especially for example on the upper left corner, the active region, they are very different, and also for the polar regions. So, and this is the correlation between these two magnetic field maps. So the correlation is very bad. If we consider the effect of non-SF integration, and if we assume that the magnetic field we derived from UCoMP is actually the result of non-offset emissivity weighted magnetic field, then we can compare the measured results with the one from the PSI model. So here on the right, it is the non-offset emissivity weighted magnetic field from the PSI model. And we can see there is a lot of similarity compared to the comparison between observation and the single slice of plane of sky. And the correlation between these two maps are much better than the previous one. And so this is a result from the comparison between the measurement and the Coronal model. But this is not very straightforward and not very consistent. So we want to do something from the point of view of the forward modeling. So using awesome model, because there are urban speed information in the model, and if we assume the random distributed initial phase on the boundary, which is a photosphere, and we can then trace the field lines to obtain the 3D distribution of the wave amplitude and the phases in the entire model. And then we can synthesize Doppler velocity time series similar to what we can observe using UCoMP. So here on the right, this is a synthesized Doppler velocity movie, which is quite similar to what we can observe using UCoMP. And if we apply our 2D Coronal seismology method to the synthesized signals, and we can also obtain a magnetic field map. So here on the left, this is the Coronal magnetic field map obtained using the Coronal seismology method based on forward modeling. And on the right, it is the non-offset emissivity weighted magnetic field in the awesome model. So here we start from the model to synthesize this signal and do the forward modeling, and we can compare them with the actual physical parameters in the model. So this is more self-consistent, and we also find this kind of relationship that the measured magnetic field using 2D Coronal seismology for UCoMP observations is very similar to the non-offset emissivity weighted magnetic field in the Coronal. So in summary, use this 2D Coronal seismology technique, we can get the global map of the Coronal magnetic field. And we also did an attempt to perform routine measurement for the global Coronal magnetic field. And a comparison between the measured results with the model shows that the measured magnetic field from COMP and UCoMP should be the non-offset emissivity weighted parameter in the Coronal. This is not only for magnetic field strength, but also for density. And we also find some very strong relationship between the measured magnetic field direction and the non-offset integrated non-offset emissivity weighted direction in the Coronal. And also based on awesome model, we synthesized the UCoMP-like wave signatures, and we can apply this Coronal seismology method to validate this method using forward modeling. And in the future, because we can obtain this kind of so-called plane of sky map from UCoMP with wave observations, and if we combine these maps with those non-offset magnetic field results from decades, or in the future use Cosmo, we can obtain both of them in a single instrument. And this is a possible approach to retrieve vector Coronal magnetic field for the first time from the view of observation. Thank you. Questions?
Question. If I saw that right, the emissivity wave maps come up with a lower level. Is that correct from what you had gotten from the your analysis in UCoMP, or did I look at that one?
In You mean by this kind of weighting, we
Yes.
should expect some lower
Yeah,
magnetic?
yeah, that's what I thought I saw.
Yeah, I think it is true. And
That's why if you want to comment on that, because when you, the last set of maps you display, not that one. That, those field strengths look a little bit low. I just wondered if you want to comment.
yeah, here the color bar is the range is from 0 to 3 Gauss, but actually, if we take a look at some very specific regions, sometimes we can see field strength as high as like 20 Gauss, but uh, but for most regions they are around like 5 or 6 Gauss, something like that, or even lower.
It seems that the simulations you use don't have as high a spatial resolution
Yeah.
as the observations.
Yeah, so that's why we cannot see this kind of fine structures as what we can see from observation.
Yeah,
Some of the thermodynamics of the model and whether it's going to localize in that way. These are global models.
Yeah,
Like,
so it's
I have an objection and out of that question. You say the modeling is validating these observations. Shouldn't it be the other way around? Because the coronal magnetic fields are being modeled under a certain limited physical assumption that are not strictly fulfilled, whereas a real observation is that what physics should do. So it should be shouldn't it be the other way around?
yeah, I'm not saying that the Coronal models validates the measurement. I'm just using forward modeling to validate this method to say that we get we get some real accurate results using this method. Because we are
technique.
yeah, we are validating this technique to say it's correct. And of course, the observation should help improvement in Coronal models.
You're comparing model to model, not model to observation for the validation of the
Yeah, for the
technique.
validation, we are starting from the model, not from the observation.
Okay.
Yeah.
Right.
I just have a question. I think it's probably the line of sight. What is the quantity? What exactly is the quantity mean? It's basically shown as I think you expected, and I think that the quantity this number B is somehow an average number through a line of sight.
Yeah.
So when you talk about combining the deepest line of sight map to get a vector holomagnetic field, I guess it's important to point out that that quantity itself will pretty much be this average number.
Yeah, so that's why I'm trying to use forward modeling to both synthesize the plane of sky and line of sight magnetic field to see if we can really get the accurate vector magnetic field. But because of the line of sight integration is not only for UCoMP wave observation, but also for Stokes wave observation, because I can see some very simple results here. So here I use the PRC model to synthesize Stokes wave, and here on the lower right corner, this is the comparison between the measured line of sight magnetic field with the exact line of sight on the plane of sky. And we can see some discrepancy, but if you take a look at the upper panel, this is the comparison between also the line of sight weighted results with the line of sight measured results, and they are more similar. So for all, I have to say for both decades and UCoMP observation, we all have this issue. So if we want to get an accurate vector magnetic field measurement, we should look at some structures that are very standalone, have very standalone emission, dominating emission on all the line sides, rather than some very diffused region. So I think that's what we need to seek for future observations.
So you, and we kind of, this is not surprising, right? I mean, we knew it was going to be this, this anyway.
I just
But
wanted
it's great to
bring
see
it up.
it.
We're on the same.
It's great to see it demonstrated, but go ahead.
Oh, it's nice. I think the results are very nice. I just wanted to ask the question, what to know. That's all. I can see you have to get an accurate vector dynamic field. Does that mean an accurate measurement in a single region?
Yeah.
Versus actually, can we ever? And this is what Max Kramar's work is trying to do, is actually you need more data to populate the numbers along the line of sight. But I'm not sure the answer. I'm not sure I have an answer.
You're right, that the real vector is going to be more complicated. And if this is, but they're
Yeah.
both going to be in somebody weighted, so, yeah, pretty.
Two quick comments on that. Totally agree, but I also think that, as you know, that the structure like a cavity, which is extended along the line of sight with a symmetric structure, you can get a meaningful, because your weighted line of sight thing is telling you about the axial field of flux type structures. You don't need a localized structure in cases like that. And the other thing is, I think there's tomography is one way to do it. And the other way to do it is to start with a global model and adjust your model in response to the data. So you optimize in response to the measurements.
Yeah.
And then that's another way to get the 3D field, to get the 3D field out of something which is because you're forward modeling, and that takes care of your weighting along the line of sight, and then you're adjusting your model. And again, you combine that with some,
And hope that thing is dominating the line signal. It's just that, it's hard sometimes to prove that, to isolate the structure. That's all.
yeah. I mean, the question is how much data and what kind of data do you need to really close? And that's, I think, the open question. Right?
And actually, for UCoMP observations, because we have a series of different maps within a solar rotation, we also tried to do the tomography for magnetic field gas. But for tomography, you need to know the relationship between the matter with what's the ion integration. So here, so we assume that it's ion emissivity weighted, and we did a tomography, and we found the results are not even as good as this map. The simple stacking of different maps, if we do tomography, the results are not as good as this one.
In what way are they not as good?
Comparing with photospheric magnetic field.
So one thing, and I think we talked about this at one point, you notice what you would expect actually is for that strong field to change latitude, because you're looking at a higher radius, right? This is at this photosphere and at 1.15, so you wouldn't expect them to overlay exactly, especially the strong loop type structure. It'll get shifted.
But for that tomography results, the results are really different. So, so you see very strong patches in what you should expect a very weak field region.
Gotcha.
So I think there may be some problem with tomography for this kind of coronal magnetic field using the wave observations.
There's challenges there.
But we did have some results.
Well, let's thank Zeno again.